Good morning. I'm here with our last lesson of our little mini unit here before winter break. There we go. Go ahead and get our... Why is that not working? Because it's me. Try again. Oh, there we go. Nothing like a Willenbrock video to start things off. So we're going to talk a little bit about differentiability. Derivatives, where functions have derivatives that don't exist. All functions have derivatives, but there are potentially some locations on a function where you can't calculate a derivative. Sometimes it's good to, when we're talking about this, to think about derivative as a slope. Okay, so another way to say this would be sometimes there's places on a function where we can't legitimately calculate the slope. There are visual clues on certain functions that tell us that calculating the slope there is going to be a problem. And the first part of this is going to illustrate some of those. So a good example of this is an absolute value function. That sharp point onto the absolute value function, we're going to call a corner. And a corner is a place where it's troublesome to try to define the slope. Okay. If we were standing right here, how do we consider the slope? You know, if I'm at this point right here, if I'm right there, I'm on this side, and my slope is 1. If I'm standing here, my slope is -1. But if I'm right on this corner, what slope do I talk about? Which is my slope? Okay. Another way to illustrate this is if we graph these slopes. Okay. So here's how to think about that. So f prime, remember, are the slopes of f of x. For this particular function, and I'm going to go to a new page for this, an absolute value function is really a piecewise function. It's equal, an absolute value is x is equal to x. When x is greater than or equal to 0, it's equal to the opposite of x when x is less than 0. And so if we were going to translate this into derivatives, the derivative of x is just 1. The derivative of negative x is -1. So my derivative for the absolute value function is also a piecewise function. The derivative of the absolute value of x can be two different things. It's 1 when x is greater than or equal to 0, and it's -1 when x is less than 0. Okay, you might need to pause and think about that or watch that again. Absolute value of x is really the function that has two pieces, which has two distinct derivatives, which graphically looks something like that. We don't have a derivative or a defined slope at x equals 0. And the reason, it's not because of this not having a solid point on the derivative. It's the continuity problem. Because the derivative, if we look at the derivative function, where the derivative function is not continuous, that tells us the original function doesn't have a derivative at that point. Doesn't have a defined derivative. And so we would say it's not differentiable. A sharp corner will do that. Another version of a sharp corner is something that looks like that, where it comes to the point, but it comes curved. That's called a cusp. Some textbooks call them both corners or both cusps. College Board is fine with you using either word for either visual presentation. Okay, so one of the things that makes a function not have a defined derivative at a location is if the derivative function is not continuous at that location. Cube root of x is another one, and I'm gonna kind of really overgraph if you graph a cube root of x on a graphing tool and you zoom in on it, you're going to see something that looks more like that. I'm going to try that a little better. Okay. I always have that second part is always. So what happens is it's very, very almost vertical before it goes out there. So that like vertical section, a lot of times we talk about, is where the tangent line would be going vertical. And so the slope, essentially, right around that location is undefined, and the derivative is undefined. Now, that can be hard to just see. So oftentimes, if College Board is expecting us to visually identify that, they will do something a little extra on the graph to kind of show us like, hey, it's vertical here. Or they'll literally tell us like, hey, check out this graph. It's vertical on this one little location. Now, if we look at this algebraically, the cube root of x, or x to the 1/3, the derivative would be 1/3 x to the negative 2/3, or 1 over 3x to the 2/3, that's undefined at x equals 0. We've already given you the derivative graph because we didn't want to go through trying to figure out how to graph that. But you can see, once again, we're going to have a problem. It just happens to be, again, at x equals 0. That's not the only place we can have a derivative issue. But this time, we have a derivative issue again. F prime of x, not continuous at x equals 0. Not even defined at x equals 0, but more specifically, if you kind of want to be more general, we're not continuous. Two different kinds of discontinuity. This is the infinite kind of discontinuity. This is your jump kind of discontinuity. The third thing that can happen, so two visual presentations, a point, a corner cusp scenario, a essentially vertical section, and then here's the third part. Now this one's a little harder just to identify from the equation. I'm going to graph this real quick for you. So here's, I don't know why we have it this way. So when x is less than or equal to 4, it's this line. And then when x is greater than 4, it's this line. So in this case, the original function is not continuous at 4. If we don't have a continuous function at a location, we're automatically going to not get a derivative. f of x is not derivative at, or is not differentiable at x equals 4. And the underlying reason is that f of x itself not continuous. If we don't have continuity, we can't have a derivative. If we don't have continuity at a point, we can't have a derivative at the point. And if I graph the derivatives, I mean, you'll see the derivative is also discontinuous. So my derivatives would be, for x minus 3, the derivative would be 1. For 3, the derivative would be 0. 1, 2, 3, 4. So I've got something like that. And then something like that. But once again, we did not need to look at the derivative function to know there was going to be a problem. Ooh, that's a problem right there. Me moving my notes. The fact that we had this kind of discontinuity means no derivative. This page summarizes all of those conditions, and it shows it in this picture. This problem is for you to try answering, and I would encourage you, this is a nice curve at the top, but this is definitely more of a corner location. So I would say go look at the key or at this note handout and see what I've come up with for these solutions, and I'll be happy to discuss with you if you have any questions how this worked. All right, stay tuned for part 2.